Hey everybody, this is Mr. Mazzoro, and today what I want to do is I want to leave our talks about the general pelagic ocean aside and talk specifically about the organisms that live in it, and even more specifically about the fish that lives in it. There's two general types of fish that live in the ocean: fish that have skeletons made out of bone and fish that have skeletons made out of cartilage. These are separated into two general groups called bony fish and cartilaginous fish. Kind of in the layman's terms, a bony fish is what you typically think of as a fish. Cartilaginous fish are sharks, skates, and rays. They have their skeletons made out of cartilage. And today we're going to start talking about how you tell the difference between sharks, skates, and rays, cartilaginous fish, and all other bony fish. We're going to do this first externally, just what external features differentiate a shark from a regular fish, a fish with a skeleton made out of bone. Then we're going to talk about the fins that both these animals have and what their functions are. And specifically, we're going to focus in on the caudal fin, the back fin, and talk about how the caudal fin can be modified to help that organism swim through the water. There are 5 essential differences that differentiate cartilaginous fish and bony fish, differentiate sharks from fish with skeletons made out of bone. The first is where their mouth is. Sharks, or cartilaginous fish, have a ventral or bottom-facing mouth. This gives them the appearance of having a nose right here, because they have a frontal kind of protrusion in front of their body. Bony fish don't have a nose, because their mouth is terminal. It's always at the end of their body. Also, the gills of these animals differ. Sharks have spiracles, or holes, behind their eyes, and you can see each one of their gill slits. They have external gill slits. Bony fish have no spiracles, and they have covered gills. What's a spiracle? It's this hole in the back of a shark's eye that it can open to let in water. It looks like an ear, but it has nothing to do with hearing. Instead, it can be opened to let water through this hole and necessarily pass over its gills. So it's actually a hole that helps the shark breathe without having to open its mouth all the time. Bony fish don't have spiracles because they have covered gills that can flap and pass fresh water over the gills for them. Cartilaginous fish, sharks, skates, and rays, they typically have stiff pectoral fins. The reason they have stiff pectoral fins as opposed to bony fish's flexible pectoral fins is because those pectoral fins actually act sort of like airplane wings, providing lift to that animal as it cruises through the water. It needs these stiff pectoral fins that provide lift because inside it doesn't have a gas-filled swim bladder. Instead, it just has an oil-filled liver. And oil doesn't provide as much lift in the water as gas, which a bony fish has. And as a result, it needs modified fins to help provide that extra lift that it doesn't get through its swim bladder, its lack of a swim bladder. Also, the scales of the organisms differ. Cartilaginous fish have rough, sandpaper-like scales, what are called plasioid scales. Bony fish have smooth, rounded scales, what are called cycloid scales. And there's your $10 words for today. Cartilaginous fish have an asymmetrical or heterocercal caudal fin. The upper lobe of their caudal fin is larger than the bottom lobe. Again, modified fins to provide lift to that organism. Bony fish don't need that extra lift. They have a swim bladder, so they have a homocercal caudal fin or symmetrical caudal fin. Whether you're a bony fish or cartilaginous fish, you have 5 fins that do 5 different things. In order to really go through the fins and their function, I would have to start talking about pitch, yaw, and roll in the water. And that's because, if you're familiar with those words, that's airline words for where an airplane is in water, and that's because both water and air are fluids. I don't want to have to teach pitch, yaw, and roll. I think it's a little confusing. So instead, I'm going to sort of generalize these fin functions down to layman's terms, and as a result, it kind of gets a little messy, but just go with me, and it'll be a little bit of an oversimplification, but it'll be fine. First, one fin I don't have to simplify. It's that back fin. You might have heard me already say it. That's the caudal fin. The caudal fin of a bony fish and a cartilaginous fish is different shapes, but in both cases, their primary function is to provide the organism with forward movement or thrust. Another one you heard me say already, that's the pectoral fin. Stiff in cartilaginous fish, flexible in bony fish, but the pectoral fins in both organisms help ultimately provide that organism with steering and braking. It might provide extra lift in a cartilaginous fish, but steering and braking in both. Next is this fin down here, the pelvic fin. And this is where pitch, yaw, and roll comes in. Again, I'm not going to teach you that. So that's what we're going to generalize this fin's function in saying that it helps an organism keep balance in the water. In order to kind of get an idea of what I mean by this, picture a guy walking along a tightrope. The way his body is sort of balancing on that tightrope, not tilting too much to the sides, that's what I mean when I say a pelvic fin helps the fish keep balance in the water. Pelvic fins help the organism as they go straight along in the water, not tip too far to either side. If you will, that's roll, but again, I'm not going to teach those words, so. Then these last two fins, the dorsal and the anal fin. The dorsal and anal fin, dorsal being back, that's the fin that's made famous in Jaws, and anal fin because it's by the fish's anus, both do functionally the same thing. They both help the fish stay upright in the water. What's the difference between keeping balance and staying upright? Well, again, it's sort of the difference between pitch and yaw and roll, but for ease of kind of saying it, think of, again, keeping balance, the pelvic fin, as not tipping too far to the sides. Think of the dorsal and anal fins as helping the fish not barrel roll as it goes through the water or corkscrew. Better yet, if the fish turns, it's the dorsal and anal fin that help it basically re-navigate itself in the direction that it turns, and not just the fish turns and it keeps on going forward in the water. Caudal, anal, pelvic, dorsal, and pectoral fins, both bony and cartilaginous fish, do functionally the same thing. This looks a little bit out of place, but go with me. I'm about to teach you guys what different shapes of caudal fins do in the water. And the best way to talk about different shapes of caudal fins is to talk about Mario Kart characters, believe it or not. Anyone that's played Mario Kart will tell you that there's two basic categories of characters. There's light character and heavy characters. Light characters are really, really good at acceleration and really, really good at handling, basically maneuvering through the water. If you look at their ground ability, it's if you look at their handling, they're very, very high numbers. However, they're not very good at speed. They're not fast on a straightaway. Vice versa, heavy characters in Mario Kart suck at acceleration. They can't really get very fast off the starting line. And they don't handle very well compared to lighter characters. But they, on straightaways, go very, very fast. In other words, they're specializing in long-distance fast movement. Caudal fins are the same way. You can either get, like lights, acceleration and maneuvering, or, like heavies, long-distance swimming, but you can't get both. There are 4 shapes, and this determines whether the organism is going to be better at acceleration, maneuvering, or long-distance swimming. These 4 shapes differ according to their surface area. The more surface area a fin has, the better it's going to be able to grab onto and push off of water, acceleration and maneuvering. But the more drag it's going to have in the water, which limits the abilities of the organism to swim efficiently over long distance. Rounder caudal fins have the most surface area of any caudal fin shape. Therefore, they're the best at acceleration and maneuvering. But all that surface area, allowing them to grab onto and push off of water better, really adds a lot of drag when they try to long-distance swim. So these organisms aren't going to swim long distances. They really can't. There's too much drag to their caudal fin. In fish terms, these would be fish that live in more benthic environments like coral reefs, where there's lots of nooks and crannies for them to maneuver around, but very, very little straightaways for them to go through. Next is the truncate caudal fin. It's called a truncate caudal fin because it kind of looks like a tree trunk if you turn it upside down. Truncate caudal fins have a little bit less surface area to them than rounder caudal fins, which makes them a little bit worse at acceleration and maneuvering, but a little bit better at long-distance swimming. These are going to be most freshwater organisms that live in streams and large lakes, where there's going to be lots of nooks and crannies and acceleration and maneuvering, but there will be some kind of straightaways for them to swim through. Then we have the forked caudal fin. Forked caudal fins are less surface area still, and so even worse at acceleration and maneuvering, but for the first time, that lack of acceleration, maneuvering, and surface area allows them to be better at long-distance swimming. This is going to be most of your pelagic fish, most of your open water fish, where there's going to be more straightaway swimming than acceleration maneuvering, but it would help for them to outmaneuver a predator chasing after them. Lastly, there's the lunate caudal fin. The least amount of surface area means these organisms absolutely suck at acceleration maneuvering. So much so that they usually have really big other fins to help make up for it. Really big pectoral fins or large anal or dorsal fins, as you see in this animal. Think of sailfish. They have a lunate caudal fin. It's called a lunate caudal fin, by the way, because it looks like a crescent moon. All of that lack of acceleration maneuvering, lack of surface area means that these organisms absolutely rock at efficient long-distance swimming. These are going to be cruisers or pursuit predators in the ocean. If you're keeping track, these would be organisms with more red muscle than white muscle. The white muscle would be more fish with rounder caudal fins, power fish, acceleration maneuvering, lungers. Notice rounder caudal fins, truncate caudal fins, forked caudal fins, and lunate caudal fins are all homocercal caudal fin shapes. Therefore, they belong to bony fish only. Sharks, like I said, have a heterocercal caudal fin, not a homocercal caudal fin. This isn't good at acceleration or maneuvering. In fact, it's actually a rather heavy caudal fin. It adds a lot of weight to the organism. However, that larger upper lobe forces the tail of the organism down in the water, which forces the head of the organism up and provides extra lift, again because cartilaginous fish lack an internal swim bladder. That, along with their rigid pectoral fins, helps provide excess lift to any cartilaginous fish, any fish that's a shark, skate, or ray. So that's it with external differences of bony and cartilaginous fish. We started talking about the 5 main differences externally between sharks and bony fish: ventral mouths, sphericals, covered gill slits, rough scales, homocercal versus heterocercal caudal fins, stiff pectoral fins, that sort of thing. Then we started talking about both organisms' generalized fins and their functions: pectoral, pelvic, anal, dorsal, and caudal fins, and what all those fins do. Lastly, we focused in on homocercal caudal fin shapes of bony fish: rounder, truncate, forked, and lunate, and how some of them are better at acceleration maneuvering and others are better at surface area versus due to how much some are better at long distance swimming due to the amount of surface area that they have. Sorry about that. Keep in mind, cartilaginous fish don't have rounder, forked, truncate, or lunate caudal fins. Instead, they have a heterocercal caudal fin, an asymmetrical caudal fin, that helps provide them extra lift in the water. So that's it. The next lesson is going to be on some internal differences between the respiration and mouth, as well as the way those organisms osmoregulate in the water. Thanks a lot.